I don't know if I can finish this chapters or not because there will be like about hundreds something pages that I need to finish. So I'm going to start off because in the morning I taught the Thai section, but I can finish just only about like 100 page out of 2 hours. So let's see if we can do it until the last page. But anyway, we have just only two chapter left, which is this chapter is going to be your last chapter, chapter 6, but I divided into two chapters, which are 6.1 and 6.2. So today we're going to talk about 6.1. Most of them are related to the mechanical properties of material in construction. So basically, we use the knowledge from since chapter 1 until chapter 5, and then we combine it together and then see how we use it in the construction. Okay, so the material that we have mentioned a lot, like since the week number 1, are steel. We have like steel, we have concrete, timbers, brick, aluminiums, and this one may be new to you guys, but I would like to introduce you to here because like in the European countries, like they use it a lot for the fiber reinforced plastics or FRP. Um, Basically, what we have known, steel is going to be the ductile material, and then concrete is going to be the brittle material. Timber, we can just divide it into two mechanical property. One is perpendicular to the grain, another one is parallel to the grain, right? And aluminum is going to be the lightweight material that can resist a lot of force. Also, the last one is going to be the fiber reinforced plastic, which is the material that produce a really high uh, cooling capacities and with a really lightweight. Okay. And then our purpose is just to select it to use like properly. That's it. So we're going to talk a lot about structural steel, concrete, timbers, brick, aluminum, and FRP. So most of the time we may have seen in our Asian country, we have like structural steel, we have concrete, both material are the most used, in our daily life. But for the timber, it's going to be the one that have been used like 30 or 40 years ago. Because of the technology of concrete and steel construction, maybe not too widespread. So that's why during that past 30 or 40 years, they use timber a lot. And you, as you may know that in the past 30 or 40 years, our Asian country may not wasn't like that developed as today. So that's why they need some developing areas, and then they just cut the tree, and then that's why maybe in your house you may have the wooden chairs, a wooden table, so that the brick that we use to for the partition, in order to divide the section, but it also has. Okay, so according to the building height, we use a lot of hybrids material. In the height building, we also use aluminum, we also use concrete, we use steel. So we combine everything together to get a building. So I think right now it's going to be the highest one. It's going to be the Kingdom Towers. I think it's in um, UAE, I guess. And then in Dubai, it's going to be the Burj Khalifa, which is the second tallest building. And then in Thailand, we also have like uh, One Bangkok Towers, and then we have this Super Tower, and we also have like Bayuk Sky Towers. Those are the top tallest building in Thailand. So we use all these kind of material in order to build this kind of high rise building. So why do we need to about the strength, stiffness, and the durability? Basically, for the strength, it's kind of straightforward, right? When you would like to use your building, you put some weight on it. For example, like that load, life load is yourself. Then you put some equipment load, and then there will be some stress occur to your material, and then that strength supposed to be less than allowable strength, right? So it's just like an easy concept, Your stress that you use supposed to be less than allowable, so you're going to have the stability to your building. For the stiffness, it's going to reduce the scariest loop of your building. For example, the stiffness, we're going to talk something about E, the modulus of elasticity. If you remember from the previous chapters, we had something called Vmax, and then but this one from the calculation from calculation from stress. And another one, we have like the V allowable. Just I said that if this one is L divided by 360, which means we don't want to disturb like we don't want the beam to bend and then to have in contact with the under structures such as like wall and stuff. And then if we for example like the purlin of the roof structures, so we're going to provide a V allowable around we allow without the bottom structures, we use L240. It depends on the structures. Okay, and if we can complete both of these, it's going to produce like the durability. Okay, so going to look safe, and then it can hold the capacity of the building. But in our recent construction, we normally just like wonder why do we need to use steel and why sometimes we use concrete. Learn this course because we're going to differentiate between these two in the construction. So as you may know, when you test for the steel, any steel type of steel, it's going to be the steel in ductile. So which means the steel has the ductile behaviors, where concrete has the behaviors of the as the brittle material. So the steel is going to have like a higher strength and stiffness compared to the concrete. But for the if we talk in normal, it may need some maintenance to the steel. So that's a trade-off between steel and concrete. That's why like in Asian, most of the time we don't really care about our building that much after we already constructed. So the one that's going to be the most popular for us is just only concrete, reinforced concrete. So what is reinforced concrete? So as you may know in the lab, right, you test compressive strength already. So it reach about FC prime, it's going to reach about 250, right? About 250 KSC at 7 days. Okay, but for the it's not FC prime, it's force, all right? For example, like force of the concrete. But for the force in bending, what's it equal? It's 10, right? For the bending F, for the bending force that you test for the beam. How many kilonewton? So you test for the cylinder is 250, am I right? Kilonewton.
Yes.
And for the bending from the beam, 110 kilonewton. Okay. Oh, pretty high, yeah, compared to the compressive strength. So if you compare it, you can see that the bending stress of the beam, it's going to resist like smaller load and compressive strength. So that's why we have a course called reinforced concrete. So the term of reinforced concrete. So the reinforced concrete means we put some reinforcement steel into the concrete. So concrete is going to be good at compression, and then steel is going to be good at tension. And then if we combine together, it's going to be balanced. Okay, that's why the reinforced concrete is the most popular one because it's cheaper than the steel. Okay, and the way to create the reinforced concrete, it's a lot easier than steel because you can just like buy material such as sand, gravels, and cement and water. You can just get from your house, and then you can make concrete, right? And then if you go to like the store close to your house, and then you can just buy reinforced the SYS training. So they're going to come and then provide you this catalog of their constructions. I think for me, I divide the construction into 3 phases for now. The first number 1 is going to be the good old day, which means we use a lot of timbers. We use a lot of wood to construct it. And then after like about 20 years, we change to phase number 2 is we're going to use a lot of steel and concrete. But right now, if you go anywhere in Thailand or go outside Thailand, you can see that right now we use a lot of precast, like in these pictures. So for precast, what is it? Precast basically is the material that we cast in the manufacturer, okay, by the manufacturers. So it's from the factory. So you don't need to cast it at the field. So you can just like order it, and then they're going to cast for you. And then when you reach at your field, you can just like put it as a Lego. So they have like the interlocking for you guys. You guys can just like assembly it together, and then you're going to get a house, you know, for about like just 14 days, for example. But if you construct it by yourself, you know, you need to have like what we call, you need to prepare for the management, you need to call for the concrete truck, and then you need to cover it, and then you need to add some waters and stuff for the curing at the site, and then you need to wait to at least like 7 to 14 days in order to provide the strength until it reach around 90% of the FC prime that you design. So right now we start switching to the precast, which is the phase 3 of the construction right now. Okay, even though the high-rise building precast one, they're not gonna like put the brick and then put mortars and then put the brick, so they're not gonna construct that way because it's really hard to plastering. Okay, so what they need to do, they just like order it from the factory and then let they manufacture it, and then we just like, and when you reach at the site, and then you just tell the tower crane to lift it and put it on the location, and then just weld it, and that's it. Okay, so it's a lot more easier and save a lot of time compared to the manual one. And for the consideration point, as I already mentioned, so steel require more maintenance than concrete, and then you need to have also the fire and rust protection every time. Otherwise, it's not gonna stay long compared to the concrete. Okay, but for the concrete, there's nothing to worry about it. You can just like cue it, and then maybe you need to consider just only the area that you construct it. If you construct it close to the sea area, so you need to have like the cement type 5. So Ajahn Lim already mentioned about it, the one that used to prevent from the sulfate attack. Okay, so when you order it, when you construct at close to the sea, you may need to tell the cement plant that, okay, my construction site is close to the sea, so I would like to have I would like to switch from the Portland cement to the cement type 5, the one that provide high sulfate resistant to the high sulfate attack. Okay, and the second one is going to be the cost of material. Okay, if I would like to have like 1 cubic of the concrete, it's going to cost us only like 2,500 baht approximately. So right now I think it's higher than 2,500 baht per cubic meters. But for the steel, really expensive. You know, when you order it like for 10 ton, if you order it like 10 ton, you need to cut some 1 to 1.5 meters of the sample per one sample, and you need to have at least 3 sample. You know, it's already in the midterm exam, so you need to cut at least 3 sample and then test it at the lab. Okay, so these are the costs that we need to compare, which mean concrete is way more cheaper than the steel, but the steel just can be work faster than the concrete. It depends on the owner of the project, and if they say that, okay, this project I would like to make it faster, so just as the designer, we can provide them the alternative by using the steel instead of concrete. So it depends on you guys in the future. If you deal with the owner that they would like to get things faster, just go for the steel. And if they would like to get things cheaper and then longer in constructions, you can just provide them the concrete design. And number 5 is going to be the one that you need to know is the construction management. You know, you may need to know about the sequence of the construction. You know what's going to be go first, and then the hard thing about the concrete is, for the concrete, you need to prepare a lot from the site. You know, you need to prepare formwork. Do you know formwork? Formwork is the one that you need to prepare it first and then put the steel inside in order to block. Okay, so you need to prepare the formwork first, you know, and then you need to tie the reinforcement. So if you compare with the precast, and then if you compare with the steel, you can see that it's going to be a lot safer in time, you know. Okay, and lastly, it's going to be 2 of these are the one that we already mentioned. So you guys need to know what are the specification or the code, and then you know how to test it. So these are your main decision over here in order to check and then accept the material. Okay, for example, like if you would like to construct like a column, you know, for example, if I pick this column, okay, at the C area, so I just pick this column. Like for the normal structures over here, Okay, we're going to have the covering just only like 2.5. So the covering basically is the distance that cover the reinforcement. Okay, the blue one is going to be the reinforcement over here inside the concrete, and then the distance between here to here is the covering. Okay, covering is the distance from the edge to the reinforcement. Okay, that's what we call covering. And then if it's in like the normal location, like for example at our location without sea contact, we can just use 2.5 centimeters or 25 millimeters. But to prevent corrosion from sulfate attack, like at the sea area, okay, so we need to use about like 75 millimeters. Okay. So the section over here is going to be a little bit bigger in order to block the sea waters to get through our reinforcement. So that's why we need to increase it to 75 millimeters. Okay. Next up, we're going to talk about like the reinforcement steel over here. So reinforcement steel, basically it starts from the iron ore over here, and then we're going to convert it into pig iron, and then the pig iron just like furnace, and then we would like to we can add percentage of the carbon in order to produce the steel. Okay, so like in Thailand we have like a lot of good companies such as BSBM, we have SBI, and then also SYS is the most famous one, the Siam Yamato one. So if we talk about like the carbon content, you can just like check it from here. So these are the chemical composition that we already talked like from the previous chapters. And then we have they need to specify, you know, the classification for this one as 400, 490. It basically come from the yield point, ultimate point that we already mentioned. It's an elongation. And then we have the one called modulus of elasticity. So whatsoever is percentage that they add in the iron pick, so the final production of the steel is supposed to have like the same modulus of elasticity of 200 gigapascal. So we will see it later. So these are the process of getting the structural steel. And here's the example from the structural frame. So we have like the frame over here, like the post over here, and then we have like the connecting frame on top like this. Okay, so this one just can be free fabricate, which means they need to create it at the factory first, and then transfer it later to the site, and then just like assembly it as a Lego. You know, like this one for one part number one, and this one part number two is part number two. And then when they bring it to the site, they can just like weld it or maybe bolt it together, and then they're going to get like one frame. So they just repeat it, and then everything is going to be really much more faster than do it at the site. And then we also have, but all of these steel are structural steel. Most of it are using the hot roll steel, which from the TIS 1227. But for the metal sheet, which is the roofing mix from TIS 1228. Okay, so they use the steel from hot roll, and then they just like compress it to create some yielding to the metal sheet, and then they're going to test the material from the metal sheet according to the TIS 1228 later. Okay. All right, and if we go to the construction steel, we have two main steel. We have steel alloy and then the wrought steel. Wrought steel over here is the steel that can be really bendable, you know, which means it has small content of the percentage of the carbon into the iron ore. Okay, you know, at countryside you may have seen like this. In order to construct the boundary, we call it like that one. We use the wrought steel, which can be bendable. Okay, that steel, it can be bent. And then we have the steel alloy. Most of the time we use it for the construction. For the carbon steel, normally we use the carbon content between 0.2% to 2%. And these are things that I would like to mention. When you add percent carbon to a really higher percentage, so the strength will increase, but the hardness also increase, but the ductility is also down, which means you add more carbon, the strength increase, but the ductility decrease. Okay, similarly to the alloy steel, if you add more, also increase in ductilities, but the alloy steel is a little bit different. we use the content not over than 1.7%. Okay. All right, and lastly, it's going to be the one that we test at the lab is cast iron. Normally, they use a really high percentage of the carbon. It's between 2.2 to 4.5 because they would like to have like a really good in compression and also a little bit good in tension. When we use it for the railway construction, it's really good for breaking the train. Okay, lastly, what I want to mention is over here, right? This graph. So whatever percentage of the carbon that you put here, whatsoever in here, we're going to have the same slope of the linear. So the Young modulus over here is going to be always the same, around 200 gigapascal over here. So whatsoever carbon content that you add over here, nickel alloy whatsoever, for the steel, you're going to have the same slope over here. Okay. All right. So we have like many type of the percentage of the carbon that we use, but most of the time in our civil engineering, we're going to use just only two over here, very mild and then mild A36, and then we use the percentage carbon by here. So we have like steel plate, steel wires, and then steel tie, and then we have for the mild steel, our construction steel, okay, that we normally use. But for the medium hard spring and tool, we use it for normally we not practically use it that much because it's in mechanical engineering application most of the time, so we can just neglect it. But if I ask which one that you use in the construction, you're supposed to answer two of these. Okay. All right, so the second one is going to be the mechanical properties of the structural steel. So this is in conclusion, right? So if we add more carbon, the strength increase and the hardness also increase and the ductility is going down. Okay. For the alloy is the steel that going to combine some, we're going to have some permanent strain over here, and then this zone we call it the strain recovery. Okay. During the strain hardening for the cold rolled steel, so it's going to produce a really higher yielding stress, okay, compared to the normal steel. But what it lost is just the energy absorption, okay, which is less toughness. But when you pull it and then release it, pull it and release it for a few times, so your material is become more brittle, okay, than ductile. All right, so we have like the steel production for the hard work process. So you can just like YouTube it or Google it. So they're going to tell you the process how to do it. And then this one already mentioned in engineering material. So it's going to be similar thing over here. And hot roll is the one that I would like to mention because we use a lot in our CE application. For example, like for I-beam, H-beam, channel, L, and then cut beam over here. And then the sheet pile. And then we have, for hot roll, we have deformed bars, and then we have also round bar over here. Deformed bar is the one that you test at F1, and round bar is the one that has similar, not similar. Round bar is the one that good at ductility, which provide a lot of force to resist the shear stress. Okay. And for the cold working process, you're going to see some structures that really thin, you know, compared to the hot rolling process. And if we compare again, we have, if we look at the type of the construction again, we have structural steel, and then we have reinforcing steel or rebar over here. So what are the different? So for the structural steel, basically it used in a really light structures, for example, like beam, column, and truss or whatsoever. And it generally give you a few shape to pick up for the usage, such as like H or wide flank. In Japan, they use, in Europe, they use W section. But for us, we use H, like because we follow the JIS standard. So we just use H, and then we use I section, we use C channel, and then we use the L section. So we're going to get through in detail over here. So why we call it H section? If you write a letter H over here, which means most of the time, the section is going to be the same in B and D. So the depth and the width is going to be the same. But for the I section over here, normally the depth is larger than the width over here. So that's why we just differentiate it by using H and I. Okay. And then we have few more type of material. We have L, we have C, and we have T. So you're going to learn this again with Ajahn Mongkon, for the next trimesters. Okay. And for the section over here, we have the W section, which provide some note after the word W. W is the shape of the section. 300 is going to be the depth over here. And then at the back over here is going to be the weight per kilogram. So this is how we differentiate it. Similarly to I, we have depth and then we have weight. And this one we have C, we have the depth and then we have weight. And then L, we have the depth and then width and then also the thickness. And sometimes they also provide the weight over here. It depends on the draftman. So in material testing, we divide the steel just into two parts. The first one is going to be the dimension and weight, and then the second one is going to be the elongation. So the weight of the steel, what I want you to know is just the unit weight of the steel. Okay, this one is really general, so you guys need to remember it. It's going to be 78500 kilogram per cubic meters. And for the reinforcement steel, reinforced concrete, it's about 240 kilogram per cubic meters. Okay, and then strength and elongation is the one that we already talked. We talk about yielding, ultimate, percent elongation, and the Young modulus, and sometime we're going to talk about the energy. Okay. All right, so this one we cut the sample like this, and then we put it out at the lab, so we can just draw a strain diagram and we can find the property over here. Okay, so these are the table from TAS, just the example, for you to for them to reference it. So this one is the minimum from TAS, so they need to follow the grade over here. Okay. Form steel over here, we also have like the grade, the yielding stress, similarly sigma y, u, and then we have like the thickness, we have the gate length over here, and then we have the percentage elongation. So they also specify the minimum strength from ITS 1228. So for the hot form steel and then the cold form steel is going to be two different properties, in order to catch up with the minimum allowable. And then we also have like different steel, for example, like the flat and square steel, like this, the flat. And then we have some minimum property that we need to check. We have 3: yielding stress, ultimate stress, and percentage elongation. And we also have the mechanical property of the hollow section for the construction purpose from ITS 107 over here, which has the new version in 2561. And then they just like specify 3 of the stress or strain that they need to get at least for selling in the market, which are the yield stress, sigma y, and then sigma ultimate with the percentage elongation over here. Okay, so this is the section of hollow. And then moving to the next one, I think I'm going to finish this, and then is it okay if I record the video and then upload and you study later? Because I think maybe it's too hot, getting hotter nowadays. So I'm trying to finish the steel section first, and then for the timbers and others, I'm going to record it later and then upload into the system today, into the YouTube for you guys. For the reinforcement steel, for the reinforcement steel, basically we have like just a few of it. We have one is deform bar. Do you know what is deform bar? Have you ever seen deform bar? It's from F1, the one that you tested, right? So the section is going to look like this, right? It has some shape in order to bond with concrete. And then we have another one is a round bar. What is the difference between round bar and deform bar? Is just round bar is just only the sphere shape, in circle. So their surface is going to be flat. Okay, there's nothing adding on for bonding. Okay, but it's used in 2 different purposes. This one is going to be for the main structures, main steel, and this one for the shear resistant. So in concrete, most of the time we construct a beam like this because For the beam, it's going to have a really small in bending. So we compress it uniformly like this, W, it's going to bend. And then at the bottom, it's going to experience the tension over here, tension. So in concrete construction, we assume that the concrete at the bottom is going to experience like zero tension force, but all the stress is going to transfer to the reinforcement over here, the reinforcement steel. So that's why we need to add steel into the concrete, because concrete is good at compression, but it's really bad in tension. And then we just like reinforce the concrete inside, reinforce the steel inside the concrete, and then we're going to get something called RC structures or reinforcement steel structures. So reinforcement steel structures, we use it because we used to resist the tension, as I already mentioned. It's because concrete is really bad at tension, right? So we add some steel in concrete in order to resist the tension. And then we also can reduce the creep by the temperatures, and then it can also use to be prevent the crack in the concrete. And then there are some note for you guys in order to read from the rebar, right? So when you go to F1, I don't know if people already mentioned about it or not. There are like just only 3 points that I would like you to 5 main point before testing. The first one is measure the length of the sample. The second one, weight it. Okay. The third one, observe the size by look at over here. RB means round bar. So it's going to be the round shape bar. Round bar. Okay. 25 over here is the diameters. Diameters in millimeters. Okay. So RB, which means round bar with the 25 millimeters of the diameters. Okay. And then we have the trademark over here at the middle is going to be the company trademark logo. And then we have, lastly, is going to be the symbol of the grade. So SR over here is specify the strength of the steel. SR is for the strength of the round bar. Okay. And then we have 24 over here. We're talking about the yielding stress. It's going to be 2400 KSC, or it's going to be 240 megapascal over here. Okay, this is how we read it. So we have 5 main points, right? Before we test it, we observe the material first. Okay, and then number 4, weight it. Number 5, measure the length. Okay, before testing. All right. So and then we have one more thing that we would like to consider is the bending test of the steel. Okay, if you look at these figures, you can see that we need to test the bending of the steel about 180 degree over here, 180 degree. So a good steel supposed to not showing any cracking at the surface over here. When you bend it, it look normal. Okay, nothing happened to it. It's just bend in shape, but there's nothing happen. But for the bad reinforcement steel, have you ever heard the steel that has the grade SD, for example, like SD40, and then it has the T at the back? So that one is the one that really famous. Like it's like a top of the town topic from the building that collapsed from the earthquake from last year, like in Bangkok. So they use the steel with T at the back. Okay, so the T at the back mean they use they cold, they reduce the temperature, during the construction. Normally, after we do a hot roll steel, after we finish it, we just like let it about like 10 to 12 meter, and then we cut it, and then we just let it in the air in order to release the heat by itself. But for the T steel, because of the time that we release the steel to get cold by itself, it take too long, right? So they have like another type T over here is the cold temperatures by water spray. So after they finish it, extrude it, and then they water spray the steel in order to reduce the temperatures of the reinforcement rapidly. So that's why sometimes the reinforcement steel with the grade strength of the foam bar with the T has some problem during bending. Okay, so I think some of the department in Thailand, like the department from highway, they also refuse to use the steel with the grade T over here because it's not really good at bending. if you bend it here, okay, why do we need to consider about the bending over here? If you look at the one that I just write down over here, when we use it in the construction, you need to bend it like this in order to have a good hooking and then have a good bending to the concrete. So that's why we need to bend it 180. But when you bend it and then it shows some crack over here, which means it at strain hardening zone. But we don't want it to be in strain hardening zone. We would like it to be in like a normal condition, you know, without applying any load. That's why we need to consider about like bending. So how we test it? So normally when you get the sample from the lab, cut about like larger than 50 centimeters of the steel, and then what you need to do, just put the steel like this. So, and then you just apply the load at the middle, and then your steel is going to bend like this, 180. Okay, and then you observe it. If there's nothing happen like in the image over here, so your steel is okay. Okay, so if it shows some crack and then show some deflects on it, just reject that lot. Okay. All right, so these are things that you need to observe. So this one is going to be in the examination, of course. And then we have the table for you over here to use. So we have size, diameters, and then circumference, cross-sectional, and mass. So this one also used in the RC1, reinforcement steel design laters. And this one is the material testing for round bar. This one is really important. What I want you to focus is the TIS20. Okay, so you need to remember TIS20. And we have here is the first look at round bar. So there's no interlocking surface on it. It's just like round. Okay. And then in order to get the diameter of it, if you remember from F1, people say that you need to weight it first and then measure the length. Because of what? Because of the shape of the deform bar, it's really hard, you know, to measure the diameters by the vernier. So what we need to do is just to weight it and then get the length of it, and then we're going to get the average diameters. So this equation basically comes from the unit weight of the steel, which is 7850 equal to weight over volume. And then the weight is still remain the same. The volume is going to be area by the length. So if I would like to find the area, it's going to be W over 7. And then what we need to do is just to pull it at the lab, similar to what we have done, and then draw the stress strain diagram. And then we're going to get the property of it. Okay. And then this one is the bend test. We use about like about more than or equal 50 centimeters of the sample, and then just bend it like this. Okay. All right. So for the deform bar, it's going to be the one with this shape. Okay. And then the shape, they also specify the ribs that's supposed to be having the angle is larger than 70 degrees. Okay. And then it's going to be similar. If you look at over here, you're going to see that they said that it is dB, which is the deform bar. 25 over here is the diameters, and then they have the trademark over here, and then SD30. SD is from yield strength of the deform bar. 30, which is the strength of it equal to stress yielding not less than 300, larger than 3000 KSC. Okay. All right. So these are some dimension of it from the TS. So if you look at the SD30, which means it has the yielding stress of 3000 KSC, SD35 3500, SD40 is 4000 over here, and then they also specify the percent elongation for you guys. Okay, so we're going to use the same equation, and then in the examination we'll be asked what is TS 20, 24, 240, 1227, and 1228, and then lastly it's going to be the EIT 1015. So I'm going to ask you one by one. Okay, so I'm going to pick like 2 or 3 of this for 3 or 4 questions. Okay, or 3 or 4 questions from this slide. Okay, to make sure that you guys know what is the TS numbers. And if you going to pursue your postgrad, so you may need to know these ASTM numbers also. Basically, it's going to be the one that used in here. Okay, similar thing, but this one is more international. Okay, so if you look at the benefit of the steel, so the steel, it's really high strength compared to the weight ratio. So it looks like heavier, but it's really good for the strength resistant, you know. And then it's really good for the high-rise building and for the long span structures because it provide a really high stiffness, and then the uniformly mechanical property, which means this one from the manufacturing, it's going to guarantee the uniform of the mechanical, so it can guarantee the strength of it. And then the high elasticity, so it can deform under loads. And then the lifespan, a really long lifespan, you know. If you look at the building like in Americas, so they have a really proper maintenance, and then it will last really long for the structural steel building. And with the high ductilities and toughness, lastly, it's going to be ease of construction. So this one is going to be save time for construction. So this number 6 is going to be the main point that we consider. Okay, and we also have like some several of the disadvantage. We have like the maintenance cost may be higher, and then we have cost of fire protection. Also the buckling of the steel if something is not usually happen according to what we design. So it's going to do some buckling over here. And then lastly, it can happen by the fatigue if you design it to be higher than the endurance limits. And then lastly, it's going to be the brittle going to occur when you design it in a, we may not experience this because over here is maybe too hard. Okay. And next part is going to be concrete. So I'm going to stop here first, and then I'm going to record this video again and then upload it on YouTube so you can just study like this because the aircon is not working. Okay. So continue to the concrete section, which is the continuous section from the structural steel. And sorry for the interruption from. So we're going to start our second session on concrete. Luckily, you guys like learn concrete technology with Ajahn Lim. So it's really easy for me, you know, to explain what is concrete to you guys. So into two main method. One is we call it cast in place. Another one is just a precast concrete. So precast is the one that we cast at the factory and then transport to you guys at the field or at the site. But for the cast in place, we just like put formwork, order the concrete, and then we just pour it at the site. So that's why we call it cast in place. And the precast concrete is the one that we usually cast it in the factories and then transport to the site later and then just assembly it. So that's why we call it precast concrete. So concrete basically, as you may know from the concrete technology, it has a really high strength but with a really low tensile strength, as you already experimented in the laboratory 7 in concrete technology laboratory. So that's why we need to add something called reinforcement. So the reinforcement term that we put the reinforcement steel inside the concrete in order to increase the tensile strength into the section of the concrete. So that's what we call it RCE, reinforced concrete, right? So if you look at here, so we have over here, we have some girder over here is the precast section. And then if you look at the picture on the left, is they are like now pouring the concrete over here. Okay, they are pumping the concrete from the bottom and then just like pour it on the slab. So that's what we call it cast in place. And then some part of the bridge construction we use section because it may be a lot more easier, you know, just like put it on the. So these are some dam or bridge or high-rise building all around the world, you know. We also use concrete. So it's really easy for me again, you know, to explain what is concrete. And in the concrete, we have the term called cement paste. As you may know in concrete technology, cement paste is going to be the cement plus waters only. Okay. When you use cement plus waters that you test already on the lab, like 5 on the lab. Yeah, I think lab 5 of your concrete labs. So you test for the property of the cement paste already. Okay. And then for lab 7, that you just mix the concrete like before Songkran days, you can see that when we mix the concrete, we're going to use the cement paste plus gravel or coarse aggregate, and then plus the sand, or in the term we call fine aggregate. So if we sieve this properly as you did at the lab, so the strength is going to be higher than the material without sieving. And the concrete is hardened when it's in contact with waters. And then the reaction between clustering and hardening, we call it hydration process. Okay. So I don't need to explain anymore because I'm explaining the hydration process. So these are some chemicals. So I'm not going to show you the equation that Ajahn Lim did in the lectures. So I'm just showing the mass of the content over here. And then normally you already test for the harden of the concrete, the labs that you went back at 10 p.m. Okay. So you start mixing at 4 p.m. right? And that day you went back to your dormitory, and then you said that you finish it at around like 10 p.m. So in order to get the final setting time, so it spent about like 6 hours, to get it hardened. But when we get it hardened, which means the hydration process is still processing, but they recommend you to take the mold out within 24 hours, because of at the edge or at the inside of the mold, it's still having some moisture. So if you take the mold out before 24 hours, so you're going to break the angle. Okay, so you're going to defect your sample. So that's why we need to take the mold out approximately at least like 24 hours in order to make having like less deflection as possible. And then the strength and stiffness, it depends on the concrete mix design that you already did it according to the ACI at the lab. So people told you how to do it already. Some location, and then they test for the chemical, or they test the rock when it has really high limestone content. So they just pick that location most of the time at the mountain area. If you go to Bangkok, you can see that at the province called Saraburi, that one, they explode the mountain a lot, because those mountains are having a lot of content of the limestone content. So that's why they just like pick that location in order to create the cement plant over there. Okay, so to process it, really easy. Take it from the stone and then just move it to the storage and then crush it and then dry it. And then what we need to do is we can just go to the mixing. So for example, if you like to get the cement type 1, we're going to have like a different formulas for type 2, type 3, type 4, type 5. And then we're going to have different formulas. And then we're going to pass through the high temperatures rotary kiln. Okay. And then after that, after we process it, and then we're going to use, and then we process to the next one is the clinker storage, and then we prepare for the export. Okay. So generally for the concrete, we have 5 type of for cements, we have 5 type of it, which are according to the TIS 15 and ASTM C150. So we have 5 type of it. Type 1, 2, 3, 4, 5, and then the one that we may usually see the most is the type 1 or Portland cement. We call it like the general cement that we use. Okay, but when we need a really high sulfate resistance at the sea area, like the ocean area, we need to use the one called surface resistant cement, or cement type 5. And if we would like to have the early height strength, which means normally used for the maintenance of the road, or maybe maintenance of the building. So we would like to get the strength hardened really fast, okay, with a really high strength. So we're going to use type 3, and type 4 maybe for the mass construction. For the mass construction, we don't want the high we don't want the hydration to be really fast, because in the hydration process there are like chemical reaction inside, like C3A, C2S and stuff, and then those kind of chemical reaction going to produce a really high heat. So they're going to have different formulas to make the cement with the low heat. For example, like if you construct like a really high structures, like a really mass structures like a dam or whatsoever that big as like a mat foundation, so you need to use the type 4. When you order it, you need to specify to the cement plant carefully. Okay, and the second one may be not that much different from the first one. That's why it's not really that famous. But we have used the most 1, 5, 3, 4. Okay. So these are the image of the sulfate attacks, and these are the image of the sulfate attacks. Okay, and then for as of today is really convenient, in order to get to order concrete, just like to call the plant and then they're going to transport for you. Okay, it's really easy right now compared to like the previous all day. You need to sometime you need to make it by yourself, but right now you can just like call them and then about like an hour they're going to transport it for you. Okay, if you remember, we have like the initial setting time of the concrete, which whole. So during the first period, we call it initial setting time of the concrete. That period is going to be the period that you can cast the sample into your formwork, okay, in order to form a beam, column, and stuff. Okay. All right. So sometime if the concrete flow, as you already test the slump, right? When you test the slump when it's low, what you need to do is you need to, if you like to have the high strength, which means you need to add less water. Okay. When you add less water, what happened over here is it's the flowability of the concrete is so bad. So what you need to do is you need to use the vibrators, to vibrate the sample. And in the lab, I told you to use the rubber hammers in order to shake at the side, in order to let the concrete flow to the edge of the mold. This is the same purpose. And then sometimes we just like use it manually, in the past all day. And as of today, we still use it, like the 1, 2, 4 method, which means 1 cement, 2 sand, and 4 stone. And then it's going to reach just only string around like 150, because sometimes we cannot like control the property at the site. And then if we would like to get some like, for example, they use it for the just like the walkway, So we're not gonna use this method to construct the main structural like beam, column, and stuff like the beam, columns, or the slab. So for beam, column, and slab, right now we order is going to be a lot better, in terms of strength. And then we have the pre-stress reinforcement, reinforced concrete. Another one is pre-cast and also pre-stress reinforced concrete. Okay, so the pre-stress is going to be the one in the fourth year. Ajahn Anup is going to teach this. But these two is going to have different property, which pre-stress concrete is going to provide a really high strength than the strength of it generally higher than precast RC. Okay, we use a stone and it's supposed to be strong, durable. As of the lab 3, I guess you need to test for the abrasion of coarse aggregate. So that one we test for the durability, and then we have high compressive strength, and then stable in dimension and clean. So that's why I told you to sieve it first at a concrete lab before using it. Okay. And then if you have a good gradation, for example, like the sand and stuff, you need to sieve it first in order to remove the unwanted material. Sometimes you have some inorganic material that stick with the aggregate, so we need to remove it out too. Okay, if you can control the aggregate, everything is going to be better, because strength of the concrete most of the time come from these two. Okay, not the cement paste. The cement paste just use it for the filler. And water is over here. Water, I can just say that it just clean, just clean and clear without adding any like chemical inside it, so it can be used. Okay, then another one is going to be the purpose of the waters. So we use the waters for the hydration process, and then we use the water for wetting aggregate. The one that we adjust after we did the make design is when the aggregate, we just would like to add waters to the aggregate to make it wet, into SSD solution. And the last one is going to be the lubricating concrete mixtures. So we would like to lubricate it on top of the surface and then fill in all the water, inside the concrete, and then increase the concrete workability. And curing. Curing, we have like a lot of type of curing. For example, like in the image, they just like use the cloth and then just spray the water on top of it in order to prevent the water loss, from the surface of the concrete slab. And then just like spray the waters on top of the cloth, and then the cloth is going to keep the moistures on the surface. So this is the one. This is one term that we use to curing at the field, because we cannot like stay at the side and then just spray the water like 24/7. So they just use the cloth and then just spray it to just prevent the waters losing from the surface of the concrete. And then we have some factors, for curing concrete. We have like type of cement, we have some concrete mixtures, and then we have some required concrete strength, and then we have the temperatures and humidity during the curing. Okay? For example, look at this graph. So at the x-axis, we have something called age of testing, and then on the top, or in y-axis over here, we have percentage of the strength development of 28 days. Okay. For example, like for this one, the yellow line, the yellow dash line over here, you can see that if we don't do any curing of our sample, you know what happened? The strength can be reached about like 75% of your design. Okay, but if you cure the sample properly, you're going to see that at 28 days, it's going to get the strength at least 99% of the sample, which means the hydration process is going to increase in years, month by month. But we would like it to be close to 100% as much as possible at 28 days. So that's why we need to cure it at the field. Okay, and then also we need to cure it after we take the sample out from the mold. And then the percentage increase of the strength can be developed, 200 to 160% of what you design, in years. And then we have some like typical curing days. For some typical, we have some curing time, for some typical structures, for example, like column, beam, walls, and also the floors, house, or pavement. So we have these kind of different time of curing of the concrete sample. Okay. All right. You already test for this, at the lab. When you test for the compression, what happened is the concrete is going to fail. It's not gonna explode, It's going to fail like by cracking. And then it's going to show you something like this. Okay. It cracked by the angle of about like 50 to 60 degree, which means the applying load is slowly filling the sample. Okay. So if you test for the beam, for the tensile test, when you apply load at the middle, it's going to go up like this and then break immediately. But for the concrete, no. After you test it, reach the peak point, and then it's going to drop the load like this, which means the concrete material itself, we consider it as the brittle material, but the failures mechanism of it failure as the ductile material. Okay, ductile material. Okay, so you can see that the stress in the concrete are redistributed in the nearby area, which causing the progressive crack, which causing the progressive cracks until reaching the complete failures of it. So the complete failure of it is going to look like this. Okay, if you compress the concrete more without releasing it, so the concrete is going to fail at the angle of around like 50 to 60 degree. Okay, so the failure is failed by the failure of the aggregate. Okay, not the failure by the cement paste itself. Okay. All right. So I think this graph may be similar to what you have learned with Ajahn Lim. So you guys may know the importance of the water to cement ratio, right? So water to cement ratio, when the water to cement ratio high, for example, in this graph, this one is starting from 0.4 to 0.7. When water to cement ratio high, if you look at 28-day string, you can see that the string over here, it's about like just only 23 megapascal compared to the lower water cement ratio, it's about like 42 megapascal. Okay, so when the water content, water cement ratio high, the capacity strength of the concrete will drop. Okay, due to less cement react to waters. Okay, and then the H also important. When the H increase, the compressive strength also increase, but we need to cue it properly. And lastly, the next one is going to be the type of the cement, you know, and then the characteristic of the cement. When the cement is really fine, you know, it can be, if you remember from the first lab, so you test the specific area of the cement by using the Blaine air permeability. So that one, you test the surface contact of it. So if it is like higher, which means it can react with the waters better. Okay, so that's one also illustrate that it's very fine and it can be good for the hydration process. And then for the moisture content, when you test it, normally I would like you to get it out from the water curing about like at least 2 hours, you know, to get the surface dry. So you kind of like just test it immediately after you take it out from the waters. Okay, so when the concrete specimen moisture is high, the compressive strength also drop. And then the mixed proportion of the aggregate, so it's depends on your mix design. You know, you can mix to get like high or low or whatsoever. It depends on the designer's purpose. Okay, is the modulus of elasticity of the concrete. So the EC, the stiffness of the concrete, it depends on the compressive strength. Okay, the strength of the concrete, it depends on FC prime. It depends on unit weight. Okay, and that also depends on the magnitude and duration of applying load. Okay, so this one is really advanced, you know. But for the two main one that I would like to mention are FC prime and the unit weight. As you can see in the curve, you can see that the stress strain curve of here, you can see that the linear line of the higher strength is going to provide a really stiff linear line, which is going to provide you a really high modulus of elasticity of the concrete. Okay, it's different from the steel, right? Really different from the steel. From the steel, whatsoever is going to be equal to 200. Whatever is percentage carbon you put inside during the mixing, it's going to remain 200 gigapascal. So what that just dropped just only the tensile strength or compressive strength of the steel. Okay. And these are some standard you guys need to remember, and I may put this in the exam also. Okay, just go and check it. Okay. So if you would like to continue for your postgrad, so you may need to use this for your you may need to use this for your reference as the one that I put on the lab, the concrete lab. So you can just follow from this. And these are some size of the specimen. I already mentioned this from last week, last lectures. So this one is 150 and this one is 300. Okay, just put it in here. And the advantage of the using concrete, just like the economy. So the concrete is lower in price, you know, because of the material itself can be found easily. For example, like you can just like get the crushed stone from anywhere. You can get the sand from the rivers, and then the cement can be bought easily, you know, in the market. So the price is really you know, attractive, and then low in maintenance cost compared to the steel, and then good for architectural and engineering work, which means we can cast into any shape, you know, whatsoever. If you would like to make it square, we can just do it. If you would like to make it like really complicated, just like bend the formwork, you know, in order to get into that shape. And then it also has a really high fire resistance, no fireproof is needed, and we have really high mass and stiffness. For the disadvantage, you can see that we have low in tensile strength, but we solve it by putting steel inside. Okay, we solve for the low tensile strength, and then require formwork and bracing. We also solve it by using different type of the. For the second one, is going to be require formwork and bracing, cousin class concrete. But this one we also fix it by using precast right now. So some of the wall right now that they use, for example, like your dormitory, the new dormitory of SUT, we also use the precast wall. And then the third one is going to be the low strength to weight, which mean the weight of the concrete is really high, but the capacity that we get from the concrete is low, which means if we compare, it's going to be lower than the timbers, and also the lower than the timbers and lower than the steel. For one, it's going to be the time dependent behaviors. So concrete in long term can produce like shrinkage or maybe some creep. Okay, but it can be fixed by using the temperature steel. Okay, so these are some new way to build the building by using like the 3D printers, maybe robot in construction, using the robot in order to create a architectural wall as shown. And if we move to the timbers, as I already mentioned, for timbers, in the past, like all day, we use timber a lot, or we use wood a lot, because we are like a small group of people. In the last 30 years, we were not in a really modern technologies to have like concrete and steel. So what we need to do to have like a accommodation or place to stay, we just like cut the trees, and then using our manpower to build the building house. So that's why in like 1990 something, so there are a lot of wooden house than the concrete house, because concrete was really new to us, during that time. But right now, we cannot find a really good trees anymore, because the wood is now turning to a really high price, and just only like rich people, they can just buy it and then put into their house. But right now we also have the thing called like commercial forest, which is like plant some trees, and then cut it into a really small section over here, and as the glue laminate timber, which means we have the glue over here, and then just attach the small timber over here, small wood over here, and then just glue, and then add some pressure or uniform load over here over time, and then we're going to get a really good section like this. Okay, and it also can resist the force, as it should be. You can see that just only like one piece of the wood, it costs like 1650 in Thai baht. For concrete 1 cubic meters of the concrete, it costs only 2,500 baht. And then like in the past all day, we have like a lot of building that use the timbers over here. All right, so come across to the section of the timbers. We normally use just only two zone of the wood, two core zone of the wood, which are sapwood and then the heart of the wood. For the bark, we don't use it because it's just like an outside shield, and then the cambium layers, just like the growing layers, so we don't use it. And then we use just only sapwood and hardwood in order to cut it and then use it for the construction. So it's going to bend upward like this. We call it croc, and then going to stay straight at the first side, at the left side, and then on another side it's going to bend like this, similar to the torsion, like twist like this. And then we have another one, we call it coupe. It's going to curve like this. Okay, these are the defect in temper. If you in this, these are some effects, these are some defects for the wood. So this one we call it crack, and we have shake, and we have wane over here. Okay, These are the defects from the wood, and these defects, you know, most of the time occur by the temperature, because in the wood itself it has some moisture, but if we dry it too fast, the material is going to defect as shown here. Okay, so that's why we need to process it carefully, you know, in order to just maintain the shape of it. You may need to cure it properly, you know, and get the moisture out, you know, you get the moisture out in a really good way in order to prevent from these defects. And then, as you may know, the timber it's the autotropic material, which the strength depend on the grain in each axis. Okay, it depends on each axis. Okay, so if you test the material in perpendicular to the grain, it's going to provide you another different of the behaviors. If you test it parallel to the grain, so you're going to get one more difference of the behavior. For example, like this. So this one is going to be the one that tests parallel to the grain. When you test parallel to the grain, you can see that you're going to get this failure in as the brittle, okay, brittle material. But if when you test it perpendicular to the grain like this, okay, then you put the metal plate over here on top like this, then just apply the load. So it going to behave as the similarly to the ductile material. But this one is provide higher strength. This perpendicular this perpendicular stress is higher than stress in parallel. Okay, and then to find the proportional limit from this graph is really hard, you know, because it does not have the clear point. So we're going to use the proportional limit of the point B only. So we just like pull out the linear line, and then the point that cut the curvature between these two between this curve, this point we call point B, and then this one is going to be the proportional limit of it. Okay, so since the timber okay, so sorry that these are in Thai. So what I want you to focus is just only these two. All right. So this table. So I'm going to provide you this table later. Okay. So I forgot to translate this for you guys. So basically, it's going to be like the hardened wood, hardened timbers. This one is going to be like the medium, not too hard. So it's just like a medium stiffness timbers, and then this one is really hard, a really stiff timber. And if we compare the strength to the specific gravity, you know, we compare the strength of the timber to the specific gravity ratio, TS, you can see that it's about 150. So for example, if I would like to pick this one, the lowest one, so this one is the specific gravity. So this one is 1.05, assume it 1.0. So it's going to be 120. This is the bedding stress equal to 120, and then the flexural stress, and then divide by the specific gravity of 1, so it's going to be 120. But for the steel, we also have the bending stress, also steel divided by specific gravity of the steel, where the specific gravity of the steel it's 7.8, okay, really heavy, and it's about like 153. So you can see that if we compare the strength to the weight ratio, the timber also provide a really high stiffness compared to the steel. Okay, it's going to be like a really about like 20% less than the steel. Okay, but there will be some different disadvantage, so I'm going to mention it later. That's why we don't want to use the timbers instead of the steel. So for the timbers, I talked about this already. So we in the previous one we said that the timber has a really good tensile strength, parallel to the grain compared to the compressive strain and the shear strain. So that's why in the testing of the wood, we don't test for the tensile. We mostly test for only shear and the compressive strain only. So this one can be in the examination. Next is going to be the tensile force of the timber. Because when we test for the tensile stress, if we pull it out in perpendicular to the grain, if we apply force P to fail, and if we pull the timbers in parallel to the grain, it's going to be 10 times 10P over here. Okay, so it's going to be 10 times larger than perpendicular to the grain. For the compressive strain, so it's going to be about, if we compress it to fail, so it's going to fail as the progressive failures for the perpendicular to the grain. Okay, so it's going to fail like this. But if this one failed by force F, for the parallel to the grain, it's going to fail about like 3 to 4 times of the force F over here. Okay, which means the stress compressive strain in parallel is higher than stress in compression in perpendicular. Okay, but the failure material is going to be abrupt failures, so it's going to fail immediately after the peak load, and then for the bottom one, it's going to fail slowly as the behavior of the ductile material. Okay, so if you remember from the lab, so we test this for the long wooden sample and the short one. So the difference is just only the ratio. When the L over D ratio is larger than 10, length to depth ratio is larger than 10. So we can find the failure just only a few types. Stress in compression, stress in tension. So you can just put it in here. And then if the L over D is smaller than 10, I think this one is smaller than 10. So it's going to fail by the shear most of the time. So it's going to fail like this. Okay, like this. Okay, so it failed by the shear. So the higher of the specific gravity of the timbers, it's going to provide a really high strength of the concrete too. A really high specific gravity of the timber will provide also the really high stiffness of the timber too. Okay. All right. So if we classify the timbers, as the one that I told you over here, we classify into 5 stiffness. The stiffness number 1 is going to be very soft timbers, and the one that we use are 2 of these: medium stiff timbers and stiff timbers. And then last one is going to be very stiff timbers. But in our CE, we're going to use this one only: medium stiff timbers and the stiff timbers. So I'm going to translate this table for you later for the comparison. So this one is if I write this down as number 1, 2, 3, 4, 5. So this one is going to be 1, 2, 3, 4, 5 over here accordingly. All right. So the moisture content in the timber also matters. For example, if it is like the fresh timber normally have the moisture of about like 35 to 55, but when the proper moisture content in the timber is supposed to be at 19 percentage, which means the higher percentage of moisture in the timber is going to produce a really it's going to produce lower strength of the you can see that the higher moisture going to produce a really low strength compared to the low moisture of the timbers over here. Okay, and then we have specific gravity. We talked about this already. When the specific gravity higher, which means the stiffness also higher, the strength also higher. Okay, so the construction timbers mostly have the specific gravity of 0.7 to 1.1, and the density of it can be in between 700 to 1100 kilogram per cubic meters. And duration of the applied force also matters, and then the type and size of it also matters. Okay, and then in the construction we have like 2 sides of the timbers. We have one is the normal size, So it's the timber size that sell in the market, but it's smaller than the actual site due to the loss of moisture. So when we cut it at the factory, we call it normal size, and then we specify it in the catalog that it's going to be this size. But the actual size that we can measure after buying it, it's usually smaller than the normal size a little bit. So it can be smaller according to these numbers by its size. Okay, we also have like many type of the timbers like plank for posts. Okay, we have also for the beam joint and joists, and for the beam we also have for the beam joist stringers. And normally we use it for the formwork and bracing most of the time. So we have this one is formwork, and this one is for the bracing. Okay, and then these are some standard for testing. Okay, and then we have some important mechanical property of testing of the timbers. So you can just follow it here. Okay, and the advantage of the timber, basically it's going to be the environmental friendly, and can be reused, high strength to weight ratio comparable to the steel, provide a really stiff provide really high strength and stiffness compared to the steel, good heat insulation, and durable if designed and maintained it properly, if you maintain it properly. And for the disadvantage, still a lot, from the mechanical properties. Like for disadvantage, we cannot control the mechanical property of the timber, even though we plant the same tree, close to each other when we cut it. So the mechanical property from these two plants usually different. Okay. And then it's really sensitive to the environment. During the rainy season, it's expand. During the hot season, as April, so it's going to shortage. Okay. And also the strength during the rainy season is going to be another story, and then the strength during the hot season is going to be another story. So that's why timber is not really that usually used. But for the commercial timber, the property can be controlled. So that's why in America they use a lot of like commercial timber in order to construct their house, okay, rather than like concrete. And then we have like the creep behaviors for the long time, and then also not durable without a good maintenance. So you need to look at it like you need to maintain it properly, maybe yearly. If you see some pointed defects, you need to get through it like really quickly. For example, like if there's some like termite beating your wood, so you need to be careful of it, right? So next one is going to be brick.